hopefully. Oh, this would be the day, wouldn't it? Okay, so are you guys seeing a screen with a surface of revolution on there?
Yes.
Okay. So we will go ahead and forge ahead with surface area of revolution. And as I said, I will do my best to write as much as I can and then send you guys a hopefully better audio copy. And we'll see if we can get that corrected. Is this the first time that it's been this choppy?
Yeah, it's never been this bad before. Normally
Okay.
it's fine.
I kind of wonder if there's construction going on near my house. I don't know. I don't know what it is. What am I like? Let's not pretend I know anything about the internet and how it works. So, okay, but I will do my best to make sure that it's better. So we talked about doing arc lengths of revolution, and we're also going to look at doing a surface area of revolution by taking a region and rotating it around a horizontal or vertical axis, similar to finding volumes of revolution. But now we're just going to look for the area of the outside of the surface. So if you do a rotation and you get a spherical shape or an anvil shape or something like that, we're going to be looking at basically how much paint would it take to paint it. We're looking at the area of that outside surface. And we can go through a similar process as far as an idea of concern. We would still just break it up into little rectangles, and for those rectangles, when they rotate around, they would form what we call a frustum, and we would be able to find the volume of that and then, or pardon me, the surface area of that, and then add them all up using integration. What we end up with when we do that is surface area of revolution if your function is in terms of x and has a continuous derivative on the interval from a to b. The surface area of revolution can be found by taking 2 pi times the integral from a to b times the radius, which will actually just be the function itself, times the arc length differential, or the formula for the arc length as well. And the same is true when you're going around the y-axis if the function is a function of y, and we would have the function itself as the radius out here as well. So we can talk about going around a horizontal axis or a vertical axis, but typically for our problems here, we'll always be going around either the x or the y axis. So if we had, for example, the area is the region bounded by y equals the square root of x between x equals 3/4 and x equals 15/4. So if we look at that region, we're starting at 3/4 and we're going out to 15/4. So this is the region that we're rotating around the, in this case, x-axis. So when it rotates around out here, we would get a solid of revolution. But rather than trying to find the volume, we're looking for what would be the surface area along the outside of that shape. Now I turned it right side up, but we would be looking for surface area there. So we would need to find the integral from, in this case, 3/4 to 15/4. Of The radius would be the distance from the function back to the axis of revolution, so that would just be the height of the function itself, which would be the square root of x. And then times, we've still got to have the formula for the arc length in there, so that would be 1 plus the derivative of the square root of x is 1 over 2 square roots of x squared dx. So this guy is actually the same thing that we just did for arc length. This part is, and then this is the radius as far as this little ribbon here. Like if you had this little rectangle rotate around that axis, what would be the surface area of that tiny little disc of ribbon? Now, these guys are actually a little bit easier to simplify most of the time than the ones were in the previous section. So the integration on these is usually a little bit easier to do. And so we do still have to do the simplification, but usually not as much factorization involved. So this would be 1 plus 1 over 2 square roots of x squared would be 1 over 4x dx. Okay, so that would be 2 pi times the integral from 3/4 to 15/4. We have the square root of, if I put these two guys underneath one, or into one fraction, my common denominator would be 4x. 1 would be 4x over 4x, and then I have plus 1 over 4x. Now, before I go any further, do you have any questions up to this point? All right. So this would be 2 pi times the integral from 3/4 to 15/4 square root of x times the square root of 4x plus 1 over the square root of 4x dx. Now, this guy is just 2 square roots of x, because the square root of 4 is 2, and the square root of x is just that. So this square root and this square root would cancel, and we would have 2 pi times the integral from 3/4 to 15/4. I'm going to factor this 2 out front because I've already canceled the square roots. So I'm going to factor that 2 in the denominator out front, and that will equal what's left underneath the radical will just be the square root of 4x plus 1, and then dx. So I can cancel those 2's. And then how would we integrate this? We're just going to integrate this using a u substitution with u equals 4x plus 1. Now, if u is equal to 4x plus 1, then du is equal to 4 dx. So we would have pi times the integral. I'm going to leave my limits just for a moment in case we want to change them to u limits. I need a 4 dx in there, so I'm going to reverse it with a 1/4 out front. So I'll have a 1/4 times u to the 1/2 du. And so that will be, okay, let's see, what would my new limits be? If x is 3/4, then u would be 3 plus 1, which is 4. If x is 15 over 4, 4 times 15 over 4 is 15, plus 1 is 16. Now remember, if you change the limits to u limits, you never have to go back to the x's again. So we're going to complete this in terms of u's. So this would be pi over 4 times the integral from 4 to 16. Oops, we're integrating. Already doing that. So we've got 2/3 times u to the 3/2 from 4 to 16. And then we'll just plug and chug from there. Let's see, this 2 would cancel with that 4, and we would end up with pi over 6 out front. Then we have 16 to the 3/2 minus 4 to the 3/2. 16 to the 3/2, if you take the square root of 16, you get 4, and then you cube it, so this would be 64 minus 4 to the 3/2. The square root of 4 is 2, cubed is 8, times pi over 6. So we would have 56 pi over 6. Which is 28 pi over 3. So we didn't have to do any factorization really over here. We did still have to do some simplification with the function that's outside the function, or outside of the square root, and then simplifying the square root. But we didn't have to factor. So these surface area of revolutions, the process is usually slightly less algebraically involved, but there is still some that you need to do. Any questions? All right, so let's try setting up one more. So we're going to do the surface area of revolution. For So this one we're rotating around the y-axis. So on your paper, I want you to do a couple things. I want you to find x prime, and then I want you to find x prime squared. And then we will compare and put it into the formula that we have for surface area of revolution. I'm going to give you just a couple minutes to work on x prime and x prime squared. If you could, when you are getting an answer on those two, if you just type in the chat, okay, like ready or yeah or something like that, just so I know when you guys are getting ready to be done with it. All right, got a couple of people that said yes. If we take the derivative of 2y minus 1 to the 1/2, we should get 1/2 times 2y minus 1 to the negative 1/2 times the derivative of 2y minus 1, which is 2. So that 2 and that 2 will cancel. And so when we square that derivative, we will have 2y minus 1 to the negative 1/2 squared is 2y minus 1 negative 1/2 exponent to the second power. We're going to multiply those exponents, so that would be a negative 1. Is that what you guys got? Anybody out there at all?
I got the x prime right, so
Okay,
yes.
excellent. Okay, so when we put this into our surface area formula, we'll have the integral from, in this case, 5/8 to 1 of 2 pi times, in this case, the radius will be the function value of y, which would be the square root of 2y minus 1, times the square root of 1 plus x prime squared is 2y minus 1 to the negative 1, or 1 over 2y minus 1. So we will have to do some simplification here, and we'll have, I'm going to go ahead and factor this out front. So my common denominator underneath my radical would be 2y minus 1. So this would be 2y minus 1 and then plus 1 dy. So this one and this one add out, and we have 2 pi times the integral from 5/8 to 1 of the square root of 2y minus 1 times the square root of 2y over the square root of 2y minus 1. I just separated the fraction, took the square root of the top and divided by the square root of the bottom. And then what will happen is this guy and this guy we can cancel out. And so we would have 2 pi times the integral from 5/8 to 1 of the square root of 2y. I'm going to write that square root of 2y as the square root of 2 times y to the 1/2, just so I don't need to do any sort of u substitution. So that will give me 2 pi square roots of 2 times the integral of y to the 1/2 is y to the 3/2 times 2/3 from, in this case, 5/8 to 1. So let's see, that gives me 4 square roots of 2 times pi over 3. That's just combining the coefficient. 1 to the 3/2 minus 5/8 to the 3/2. So we eventually get one to the 3/2 is just 1 minus 5/8 to the 3/2. And I personally wouldn't mind if you left it like that. I would much rather have an exact answer than a decimal approximation. And not all of them will be kind of complicated fractions and combinations of fractions or anything like that, but a lot of them will be not very pleasant looking numbers, so don't stress about that too much.